Hemodynamics or hemodynamics is the fluid dynamics of blood flow. The circulatory system is controlled by homeostatic mechanisms, much as hydraulic circuits are controlled by control systems. Hemodynamic response continuously monitors and adjusts to conditions in the body and its environment. Thus, hemodynamics explains the physical laws that govern the flow of blood in the blood vessels. The relationships can be challenging because blood vessels are complex, with many ways for blood to enter and exit under changing conditions. Cardiac output and flow rate. The heart is the driver of the circulatory system, pumping blood through rhythmic contraction and relaxation. The rate of blood flow out of the heart is known as the cardiac output. Blood being pumped out of the heart first enters the aorta, the largest artery of the body. It then proceeds to divide into smaller and smaller arteries, then into arterioles, and eventually capillaries, where oxygen transfer occurs. The capillaries connect to venules, and the blood then travels back through the network of veins to the right heart. The microcirculation, the arterioles, capillaries. The venous system returns the deoxygenated blood to the right heart where it is pumped into the lungs to become oxygenated and CO2 and other gaseous wastes exchanged and expelled during breathing. Blood then returns to the left side of the heart where it begins the process again. In a normal circulatory system, the volume of blood returning to the heart each minute is approximately equal to the volume that is pumped out each minute. Because of this, the velocity of blood flow across each level of the circulatory system is primarily determined by the total cross-sectional area of that level. This is mathematically expressed by the following equation. V equals Q, A, where V equals velocity, Q equals blood flow, A equals cross-sectional area. Blood pressure across the circulatory system. The blood pressure in the circulation is principally due to the pumping action of the heart. The pumping action of the heart generates pulsatile blood flow, which is conducted into the arteries, across the microcirculation and eventually back via the venous system to the heart. During each heartbeat, systemic arterial blood pressure varies between a maximum and a minimum pressure. In physiology, these are often simplified into one value, the mean arterial pressure, which is calculated as follows. MAP 2/3 plus 1/3. Note: BPDIA weighted more heavily since the heart spends 2/3 of the heartbeat cycle in the diastolic, where MAP equals mean arterial pressure. BPDIA equals diastolic blood pressure. BPSY equals systolic blood pressure. Differences in mean blood pressure are responsible for blood flow from one location to another in the circulation. The rate of mean blood flow depends on both blood pressure and the resistance to flow presented by the blood vessels. Mean blood pressure decreases as the circulating blood moves away from the heart through arteries and capillaries due to viscous losses of energy. Mean blood pressure drops over the whole circulation, although most of the fall occurs along the small arteries and arterioles. Gravity affects blood pressure via hydrostatic forces, and valves in veins, breathing, and pumping from contraction of skeletal muscles also influence blood pressure in veins. The relationship between pressure, flow, and resistance is expressed in the following equation. Flow equals pressure, resistance when applied to the circulatory system. We get CO equals TPR, where CO equals cardiac output. MAP equals mean arterial pressure, the average pressure of blood as it leaves the heart. RAP equals right atrial pressure, the average pressure of blood as it returns to the heart. TPR equals total peripheral resistance. A simplified form of this equation assumes right atrial pressure is approximately 0. CO MAP TPR, the ideal blood pressure in the brachial artery, where standard blood pressure cuffs measure pressure, is less than 1/120th of a millimeter of mercury. Other major arteries have similar levels of blood pressure recordings indicating very low disparities among major arteries. In the innominate artery, the average reading is 110/70ths of a millimeter of mercury, the right subclavian artery averages 120/80ths and the abdominal aorta is 110/70ths of a millimeter of mercury. The relatively uniform pressure in the arteries indicate that these blood vessels act as a pressure reservoir for fluids that are transported within them. Pressure drops gradually as blood flows from the major arteries, through the arterioles, the capillaries until blood is pushed up back into the heart via the venules, the veins through the vena cava with the help of the muscles. At any given pressure drop, the flow rate is determined by the resistance to the blood flow. In the arteries, with the absence of diseases, there is very little or no resistance to blood. The vessel diameter is the most principal determinant to control resistance. Compared to other smaller vessels in the body, the artery has a much bigger diameter, therefore the resistance is low. The arm-leg gradient is the difference between the blood pressure measured in the arms and that measured in the legs. It is normally less than 10 mm Hg, but may be increased in e.g. coarctation of the aorta. Determinants of vascular resistance. Resistance is also related to vessel radius, vessel length, and blood viscosity, as indicated by the Hagen-Poiseuille equation. The equation is as follows. Increment P, pressure drop, gradient, micro, viscosity, L, length of tube. In the case of vessels with infinitely long lengths, L is replaced with diameter of the vessel, Q, flow rate of the blood in the vessel, R, radius of the vessel. Assuming steady, laminar flow in the vessel, the blood vessel's behavior is similar to that of a pipe. For instance, if P1 and P2 pressures are at the ends of the tube, the pressure drop gradient is. The larger arteries, including all large enough to see without magnification, are conduits with low vascular resistance with high flow rates that generate only small drops in pressure. The smaller arteries and arterioles have higher resistance, and confer the main blood pressure drop across major arteries to capillaries in the circulatory system. In the arterioles, blood pressure is lower than in the major arteries. This is due to bifurcations, which cause a drop in pressure. The more bifurcations, the higher the total cross-sectional area, therefore the pressure across the surface drops. This is why the arterioles have the highest pressure drop. The pressure drop of the arterioles is the product of flow rate and resistance. Increment P equals Qx resistance. The high resistance observed in the arterioles, which factor largely in the increment P as a result of a smaller radius of about 30 micrometers. The smaller the radius of a tube, the larger the resistance to fluid flow. Immediately following the arterioles are the capillaries. Following the logic observed in the arterioles, we expect the blood pressure to be lower in the capillaries compared to the arterioles. Since pressure is a function of force per unit area, the larger the surface area, the lesser the pressure when an external force acts on it. Though the radii of the capillaries are very small, the network of capillaries have the largest surface area in the vascular network. They are known to have the largest surface area in the human vascular network. The larger the total cross-sectional area, the lower the mean velocity as well as the pressure. Substances called vasoconstrictors can reduce the size of blood vessels, thereby increasing blood pressure. Vasodilators increase the size of blood vessels, thereby decreasing arterial pressure. If the blood viscosity increases, the result is an increase in arterial pressure. Certain medical conditions can change the viscosity of the blood. For instance, anemia reduces viscosity, whereas increased red blood cell concentration increases viscosity. It had been thought that aspirin and related blood thinner drugs decreased the viscosity of blood, but instead studies found that they act by reducing the tendency of the blood to clot. Turbulence. Blood flow is also affected by the smoothness of the vessels, resulting in either turbulent or laminar flow. Smoothness is reduced by the buildup of fatty deposits on the arterial walls. The Reynolds number is a relationship that helps determine the behavior of the fluid in a tube, in this case blood in the vessel. The equation for this dimensionless relationship is written as ρ, density of the blood, v, mean velocity of the blood, L, characteristic dimension of the vessel, in this case diameter, mu, viscosity of blood. The Reynolds number is directly proportional to the velocity and diameter of the tube. Note that near is directly proportional to the mean velocity as well as the diameter. A Reynolds number of less than 2,300 is laminar fluid flow, which is characterized by constant flow motion, whereas a value of over 4,000 is represented as turbulent flow, due to its smaller radius and lowest velocity compared to other vessels. The Reynolds number at the capillaries is very low, resulting in laminar instead of turbulent flow. Wall tension. Regardless of site, blood pressure is related to the wall tension of the vessel according to the Young-Laplace equation, where P is the blood pressure, T is the wall thickness, R is the inside radius of the cylinder, is the cylinder stress or hoop stress. For the thin-walled assumption to be valid, the vessel must have a wall thickness of no more than about 1/10 of its radius. The cylinder stress, in turn, is the average force exerted circumferentially in the cylinder wall, and can be described as where F is the force exerted circumferentially on an area of the cylinder wall that has the following two lengths as sides. T is the radial thickness of the cylinder, L is the axial length of the cylinder. Venous capacitance. Veins are described as the capacitance vessels of the body because over 70% of the blood volume resides in the venous system. Veins are more compliant than arteries and expand to accommodate changing volume. Monitoring. Hemodynamic monitoring is the observation of hemodynamic parameters over time, such as blood pressure and heart rate. Blood pressure can be monitored either invasively through an inserted blood pressure transducer assembly, or non-invasively by repeatedly measuring the blood pressure with an inflatable blood pressure cuff. Etymology and pronunciation. The word hemodynamics uses combining forms of hemo and dynamics, thus, the dynamics of blood. The vowel of the hemo syllable is variously written according to the A-E variation. Bibliography. Burnroom, Levy M.N. Cardiovascular Physiology. 7th ed. Mosby 1997. Roll Pound. Human Cardiovascular Control. Oxford University Press 1993. Brownball D. Heart Disease. A Textbook of Cardiovascular Medicine. 5th ed. W. B. Saunders 1997. Siderman S. B. R. Kleebag. Cardiac Electrophysiology, Circulation and Transport. Kluwer Academic Publishers 1991. American Heart Association. Otto the 900th, Stoddard M. Wagner A. Zobiwa. Recommendations for Quantification of Doppler Echocardiography. A report from the Doppler Quantification Task Force of the Nomenclature and Standards Committee of the American Society of Echocardiography. JMSOC Echocardiogra 2002, 15-167-184. Peterson L.H. The Dynamics of Pulsatile Blood Flow, Circ. Res. 1954, 127-139. Hemodynamic Monitoring, Bigatello L.M., Georgie, Minerva Anesthesiol, 2002 APR, 68-219-25, Claude Franceschi, Paolo Zamboni Principles of Venous Hemodynamics Nova Science Publishers 2009-01, ISBN near 1,661,859,781,681,924,853. W. R. Milnor. Hemodynamics, Williams and Wilkins, 1982. B. Boteremek. Systemic Hemodynamics and Hemodynamic Management, 4th edition, ESBN 1-59196-046-0.